Forget the serene, unchanging moon you see in the night sky. Its early life was an absolute war zone. We're diving deep into a celestial brawl where city-sized asteroids slammed into its surface, battling against eruptions that dwarfed anything on Earth. Get ready to challenge your assumptions about the moon's past and see the evidence of its fiery creation. Imagine a young moon, not peacefully orbiting Earth, but a literal inferno. For eons, scientists debated, was its scarred face molded by relentless meteor showers, or did volcanic titans erupt from its core, reshaping its landscape? The answer might surprise you. We're revealing the astonishing evidence that tells the true, explosive story of our moon's birth. The moon's birth from the Big Whack and its immediate molten state. In the earliest twilight of the young solar system, when planets were still half-formed and drifting through a haze of dust and fire, Earth experienced an encounter so violent that it reshaped both its destiny and the skies we now look upon. A Mars-sized protoplanet, often called Theia, struck Earth with a glancing, world-shattering blow, releasing energies beyond anything our minds can comfortably imagine. In the blinding aftermath of this colossal impact, debris was hurled outward in a swirling, incandescent halo that wrapped around the battered planet. From this brilliant disk of molten rock, metal, and vapor, the moon began to gather itself, coalescing like a glowing ember pulled into shape by gravity's unseen hands, its entire surface shimmering with heat for millions of years to come. The newly formed moon was far from the pale, serene companion we know today. It was a molten fireball, its surface an ocean of magma stretching from horizon to horizon, a restless, churning sea of liquefied minerals. The heat radiating from it would have painted Earth's night side a deep red glow, like a never-ending sunset burning just beyond the edge of dawn. This molten state wasn't a brief flare of turmoil, it persisted long and fiercely, fed by the energy of the impact and the tidal forces from a young Earth spinning so rapidly that a day lasted only a few hours. As the moon orbited much closer than it does now, it loomed enormous in Earth's sky, dominating it with both size and the blazing intensity of its liquid surface. At this stage, the moon's crust had not yet begun to solidify. Instead, materials within the magma ocean differentiated by density, sinking and rising in slow, turbulent currents. Lighter minerals floated upward, forming the earliest hints of what would eventually become the lunar highlands, while heavier elements sank toward the core. This internal rearrangement created a dynamic, layered structure, one that carried within it the fingerprints of the moon's fiery birth. Yet the surface remained a molten canvas, constantly reshaped by convective motion and extraterrestrial debris still drifting from the impact cloud. As millions of years passed, the outer layers began their slow transformation from liquid fire to solid rock. The cooling process wasn't uniform, nor gentle. Pockets of magma continued to simmer beneath the crust, sometimes swelling upward and cracking through the hardened surface in volcanic fountains. Even as the crust thickened, the moon was still shedding heat, radiating its leftover energy into the blackness of space. This cooling was a long and uneven descent from chaos toward the quiet stillness we now associate with the lunar surface. Earth's gravitational pull played a central role in this transformation. Because the moon orbited so close in its early years, tidal forces kneaded its molten interior like dough, generating heat that slowed its cooling. The tidal bulges created by Earth tugged rhythmically at the lunar magma ocean, elongating and compressing it over countless cycles. This ceaseless kneading not only prolonged the molten state but also helped distribute magma across the surface, evening out irregularities that might otherwise have defined the moon's shape. Eventually, as the crust thickened, the moon's surface began to bear the marks of bombardment from space. The solar system remained a chaotic environment filled with leftover building blocks, and the still cooling moon was a prime target. Each impact created shockwaves that rippled across the crust and churned the magma beneath. Some collisions punched through the thin crust entirely, creating craters that filled with molten rock before solidifying again. These early scars form the foundation of the Moon's battered, cratered appearance, though they would later be overshadowed by even larger and deeper basins. Within the Moon's interior, stratification continued as the mantle differentiated into layers rich with various silicates and minerals. The core, though small compared to Earth's, settled into place as a sphere of metallic iron and sulfur. Heat from radioactive decay also contributed to the long, slow cooling process. Though the crust appeared solid, the internal ocean of magma beneath it remained in motion, shaping the Moon's evolution for hundreds of millions of years. The Moon, once wholly molten, was becoming a world with an outer shell and an inner fire. Meanwhile, Earth and Moon were locked in a dance of gravitational evolution. The young Moon orbited much closer, perhaps only 20,000 to 30,000 kilometers away, appearing dozens of times larger in the sky than today. With each orbit, Earth's rotation slowed slightly, and the Moon drifted outward a tiny bit more. This widening distance reduced tidal heating over time, allowing the Moon to slowly stabilize into a more solid and quiet world. Yet the memory of those early, fiery years remains imprinted in the composition of lunar rocks, carrying the thermal history of an infant world. Once the magma ocean began to solidify into a stable crust, the Moon's surface took on a new form. Instead of a uniform molten sheen, it now displayed patches of hardened minerals, plagioclase crystals rising like frozen foam above darker, denser material. These plagioclase-rich regions eventually grew into the highland terrain, their pale, reflective surfaces giving the Moon much of its distinctive light-colored complexion. This early crust became a kind of floating shell, riding atop the still molten depths, occasionally cracking under stress and allowing magma from below to surge upward in fiery eruptions. Even after the crust formed, internal heat kept the lunar mantle partially molten for a long time. Deep magma reservoirs lingered beneath the surface, occasionally swelling and forcing lava to the exterior. These eruptions created basaltic plains, though the most famous ones would not appear until hundreds of millions of years later. Still, even in its youth, the Moon was far from static. Its geography shifted, bulged, cooled, and fractured, sculpting a world that was gradually transitioning from feverish creation to stark, serene longevity. This extended cooling period saw the crust fragment into a mosaic of plates, not tectonic in the way Earth has them, but sections that floated atop the mantle, shifting slightly and cracking under stress. Each fracture became a potential pathway for magma to escape, turning the Moon's early surface into a network of fissures glowing with molten light. Over time, as surface temperatures dropped and impacts became less frequent, these volcanic episodes slowed, allowing the crust to thicken further. With the passage of tens of millions of years, the Moon's glowing red aura faded, replaced by a darkening, solidifying shell that radiated far less heat. The once liquid surface lost its shimmering fluidity as crystals interlocked into rigid structures. As the molten state gave way to solidity, the crust became capable of preserving the marks of every subsequent event: impact craters, volcanic flows, fractures, and eventually the immense basins that would fill with lava to create the Maria. Though the Moon was still geologically active beneath its crust, externally it was losing its molten glow. The surface cooled enough for brittle minerals to form, and micrometeorites began peppering it with tiny scars. Each microscopic collision contributed dust to the early regolith, though it would take billions of years for the layer to reach the thickness seen today. The Moon was transitioning from a world shaped by internal fire to one sculpted by external bombardment. During this time, residual heat trapped beneath the crust continued to drive volcanic and tectonic-like activity. Magma pockets expanded and contracted, creating subtle waves and bulges on the surface. These uplifted regions would later influence where basaltic floods pooled in the Moon's enormous basins. Even though the magma ocean had largely solidified, the Moon's interior remained dynamic, and heat seeped outward in faint whispers rather than explosive bursts. Earth, too, influenced the cooling process. The gravitational interplay between the two bodies created stresses that caused the lunar crust to flex, particularly on the near side facing Earth. This flexing generated additional heat through friction, delaying complete cooling in some regions. It also created weaknesses in the crust where future volcanic episodes would later erupt, explaining the asymmetry between the Moon's near side and far side. As the magma ocean dwindled and solid rock took dominance, the Moon's moment of major geological transition arrived. The early crust, once floating above a global sea of molten stone, stabilized enough for the formation of the thick highlands. These bright, rugged terrains became the Moon's most ancient surfaces, forever preserving the imprint of the planet's earliest epochs. While later events would mar and reshape them, the highlands remain relics of the Moon's molten childhood. With increasing crustal thickness, volcanic activity became more localized. Instead of widespread eruptions from a global magma source, lava now surfaced through isolated channels, vents, and fissures. These events were still intense, but they represented a shift toward a more mature, cooling world. Over time, these eruptions would become rarer and more subdued, though they would leave dramatic geological signatures that astronauts billions of years later would walk across and sample. The Moon's far side, insulated from Earth's tidal influence, cooled faster and developed a thicker crust. This thicker layer became more resistant to volcanic resurfacing, which is why the far side remains dominated by highland terrain rather than the broad maria seen on the near side. Even in its earliest molten phases, the Moon was already beginning to express its two-faced personality, shaped by asymmetries in heat retention, tidal stress, and crustal evolution. During the final stages of cooling, the Moon contracted slightly as internal heat dissipated. This contraction created wrinkle ridges and shallow faults across the surface, geological features that still exist today. Although small compared to Earth's tectonic forces, these lunar contractions helped seal the crust, reducing the frequency of major volcanic eruptions and pushing the Moon further toward geological quietude. As the world continued to cool, the last reservoirs of molten rock retreated deeper into the mantle. The surface, once glowing like liquid metal under the infant sun, became marked by shadows, craters, and growing expanses of solidified mineral plains. The Moon had entered the long phase of bombardment that would shape its identity for billions of years, carving deep basins that would later overflow with basaltic lava and form the iconic Dark Maria. The Moon's cooling did not eliminate volcanic activity entirely. Instead, the Moon entered a phase of episodic eruptions, where lava occasionally breached the surface in fountains or slow oozing flows. These eruptions, though fewer and farther between, contributed to the layered complexity of lunar geology. They created channels, domes, and lava tubes that remain preserved in the airless silence of the lunar landscape. By the time the magma ocean had fully solidified, the Moon had become a world shaped by impacts rather than internal dynamics. The crust, now robust and rigid, preserved every collision with remarkable fidelity. The molten, turbulent world of its birth was now buried beneath hardened rock, cooled fragments, and sprawling highlands that glowed softly beneath the sun's distant light. Yet the memory of its fiery beginnings remained locked within minerals, isotopes, and chemical signatures waiting billions of years for human hands to uncover. Even long after the last magma reservoirs cooled, the Moon continued to evolve subtly. Tidal interactions with Earth gradually rounded its orbit and synchronized its rotation, forging the familiar sight of one hemisphere always facing our planet. This slow dance, forged in the furnace of the Big Whack, ensured that the Moon's molten, violent birth would eventually give way to the calm, observational role it plays in our skies today. And so, from the fiery, molten chaos born of cosmic collision, the Moon settled into its long life as Earth's serene companion. Its early molten state shaped every aspect of its surface, interior, and long-term evolution. The molten oceans froze into highlands, the tidal kneading etched internal layers, and the heat of its birth echoed across billions of years through volcanic plains and shimmering mineral records. What began as a glowing, turbulent orb has become a quiet, reflective world, yet every grain of lunar dust still whispers the memory of the fiery moment when the moon first emerged from the cosmic impact that forged it. Early bombardment, a relentless cosmic hailstorm shaping the protomoon. In the chaotic stillness after its molten birth, the young moon found itself exposed beneath a universe that had not yet settled into calm or order. Countless fragments left over from planet formation still roamed the solar system: asteroids, protoplanetesimals, shards of rock and metal drifting like ghostly survivors of a cosmic brawl. With no atmosphere to shield it and a crust still warm and fragile, the moon became a prime target for every wandering object. Each impact slammed into its surface with unimaginable force, sending molten fountains skyward and carving deep scars into the still-forming crust. This era of bombardment wasn't brief. It was a long, punishing rain of stone and fire that shaped the moon's identity before it had the chance to cool into the serene orb we now see. The impacts ranged in size from small projectiles that created shallow indentations to monstrous collisions large enough to melt entire regions of the crust anew. Every strike injected heat back into the lunar surface, keeping parts of the mantle molten even as the rest of the moon tried to cool. These collisions stirred the crust like a spoon swirled through thick, cooling soup, bringing minerals to the surface that would have remained buried deep below. With each blow, the moon's surface became a tapestry of molten patches and shock-cracked layers, a geological record written in fire and force. The protomoon's face changed constantly, never settling, always reshaping under the relentless cosmic hail. Some of the larger impacts were so catastrophic that they blasted material into space, adding to the debris cloud that continued to swirl around Earth and Moon like a vast, chaotic ring system. Pieces of the moon were torn away into orbit only to fall back again in a second wave of destruction. This recycling of debris meant some regions were hammered repeatedly, melted, cooled, and melted again. The moon's crust, though forming, never had a chance to grow still or uniform during this era. Every crater carved into its surface became a mixing bowl where ancient and new materials fused, creating the complex mineral diversity found in lunar rocks billions of years later. Throughout this violent period, the moon's near side faced Earth's glowing, post-impact heat, while the far side faced into deep space. This asymmetry meant the crust cooled unevenly, creating differences that the bombardment exploited. On the far side, where the crust thickened more quickly, incoming impactors struggled to fully melt through the hardened layers. Meanwhile, on the near side, where Earth's radiated heat kept the crust warmer and thinner, impacts dug deeper, stirring up magma and creating vast basins that would one day become the Maria. The bombardment didn't just scar the surface, it sculpted the moon's long-term geological identity, dividing it into two distinct hemispheres even in the earliest chapters of its existence. Each impact unleashed shockwaves that rippled through the crust, fracturing the newly forming surface into networks of fissures. These shockwaves penetrated deep, sometimes reaching reservoirs of lingering magma beneath the crust. When that happened, lava surged upward through the cracks, filling impact basins with glowing seas that temporarily smoothed the damage before cooling into dark, dense rock. This interplay of impact and eruption created multi-layered geological structures: crust, melt, and volcanic resurfacing layered like pages in an ancient book. Even when the crater shapes faded through later bombardment, these layers persisted deep underground, preserving a hidden history that would only be revealed by seismic sensors billions of years later. The bombardment carried not only destruction but also delivery. Asteroids and comets arriving from distant regions brought new minerals, metals, and perhaps trace volatiles to the moon. Although most water delivered by comets vaporized instantly when they struck the hot surface, tiny amounts may have survived, trapped in glassy beads formed by melting rock. These microscopic traces, found by modern researchers, are faint whispers of an era when each incoming body reshaped the Moon chemically as well as physically. The bombardment was not random chaos, it was a process of layering, enriching, and modifying the Moon's composition in ways that still define it today. The impacts also helped thicken the early regolith, though it was nothing like the fluffy surface layer we see now. Instead, the earliest regolith was a dense, chaotic mix of shattered rock, molten droplets, and crust fragments welded together by heat. Each explosion churned this layer deeper, creating a surface that was fractured, uneven, and unstable. This fragmented layer acted as a thermal blanket, helping the deeper crust cool more slowly and allowing residual magma pockets to remain active longer than they otherwise would have. Thus, the bombardment didn't just attack the surface, it changed how the Moon cooled from the inside out. As tens of millions of years passed, the bombardment intensified into what scientists now call the Late Heavy Bombardment, a period of accelerated impacts caused by giant planet migrations disturbing asteroid populations. The Moon, lacking any atmosphere or magnetic shield, bore the full brunt of this destabilized solar system. Immense asteroids slammed into the surface, releasing energies equivalent to billions of nuclear explosions. These impacts created colossal basins thousands of kilometers across, some deep enough to punch through the crust into the mantle below. The South Pole Aitken Basin, one of the largest known impact structures in the solar system, emerged during this era, leaving a scar so deep it exposed materials from layers usually hidden beneath the crust. These titanic collisions reshaped the Moon's interior by redistributing heat and creating new channels through which molten rock could later rise. The deepest basins weakened the crust in ways that would have long-lasting consequences. When the bombardment finally eased, these weakened regions became conduits for lava to surface during later volcanic episodes, creating the vast dark plains we call Maria. Thus, the bombardment set the stage for a geological transformation that wouldn't occur until hundreds of millions of years later, long after the surface had cooled. The Moon's later appearance was already predetermined by the violent sculpting of this early epoch. Every massive impact also launched huge quantities of material upward, creating temporary atmospheres of vaporized rock. These atmospheres were thin, fleeting, and soon lost to space, but in the moments they existed, they allowed particles to drift and settle in patterns influenced by gravity and temperature. This subtle airborne redistribution helped mix fine materials across wide areas, smoothing some regions while leaving others jagged and sharp. Over time, these brief episodes of atmospheric suspension contributed to the Moon's patchy surface textures. Some regions became smoother plains, while others remained chaotic and rugged. Even though the bombardment was destructive, it also acted as a sculptor, carving the Moon's topology in ways that later celestial visitors would notice immediately. The deep craters, towering rims, and enormous multi-ring basins became permanent fixtures of lunar geography. These features influenced everything from how sunlight casts shadows across the surface to how later geological processes unfolded. Every crater created a new microenvironment where solar heating, dust settling, and thermal expansion played out differently. The bombardment, in essence, created the Moon's personality. Its soft glow hides a surface shaped by unimaginable violence. The Moon's rotation also played a role during these early impacts. Because its spin rate gradually slowed due to tidal locking with Earth, some regions experienced more impacts earlier than others. As the rotation slowed and finally synchronized, the distribution of impacts subtly shifted. Areas that once rotated through space-facing positions became locked in place, receiving a different pattern of bombardment than before. This shift meant that some surface zones contain layers of impacts accumulated over changing rotational states, while others experienced a more uniform history. These differences contribute to the complex geological patchwork still observed today. Throughout this era, Molten pools from impacts cooled in different ways depending on their size and mineral content. Some cooled quickly into smooth glassy patches, while others solidified slowly, forming coarse-grained rocks rich with plagioclase or pyroxene. These rocks became some of the oldest preserved materials in the solar system, surviving untouched beneath later layers. When Apollo astronauts brought samples back, these ancient rocks served as time capsules, each fragment preserving traces of the intense heat and pressure of the bombardment epoch, allowing scientists to reconstruct the Moon's earliest struggles. Even as the bombardment continued, the Moon's crust thickened and became more resilient. The molten pockets beneath the surface diminished in number, though they remained active in scattered pockets. As the crust strengthened, impacts created more defined craters rather than sprawling melt basins. The landscape shifted from one shaped primarily by molten flows to one dominated by sharp rims, radial ejector lines, and steep walls. The bombardment did not lessen its force, but the Moon's evolving surface changed how that force was recorded. This transition marked the gradual end of the Moon's molten infancy and the beginning of its crater-dominated adolescence. Because the Moon lacked erosion agents like wind or water, every impact remained etched onto its surface in exquisite detail. This permanence allowed each new crater to build upon or distort those preceding it. The surface became a layered record of overlapping scars, each marking a moment in cosmic history. Some craters nearly erased older ones, while others landed delicately on the rims of ancient features. The result was a geological palimpsest where time itself could be read by examining which scars lay on top of which. The Moon became, in effect, the solar system's memory stone. The bombardment also created deep pockets of fractured rock called breccias, formed from shattered fragments fused by heat and compression. These breccias filled crater floors and lined crater walls, forming a jagged layer that extended deep below the surface. This fractured underlayer later influenced how moonquakes traveled and how heat moved through the crust. The bombardment not only shaped the surface, it engineered the Moon's internal acoustics, determining how its interior would respond to stress for billions of years. Though the bombardment decreased over time, its effects accumulated relentlessly. The protomoon's rugged crust grew thicker with each new layer of impact melt and ejector. Over millions of years, enormous quantities of crushed rock settled into broad regions, forming highland terrains that gleamed brightly in sunlight. These highlands became the Moon's most ancient surfaces, their brightness a reflection of the heavily fractured, mineral-light crust forged during this violent era. Their irregular shapes and towering elevations would remain as enduring markers of the early cosmic storm. Each major crater created a network of secondary impacts, smaller craters formed by debris flung outward at high speed. These secondary impacts peppered the landscape with countless small dents that contributed to the Moon's dusty, uneven character. Even small impactors created ejector blankets that extended for miles, coating distant regions in fine, pulverized debris. Over time, these overlapping blankets wove together into a complex surface layer where grains of dust carried traces of impacts that occurred millions of years apart. The bombardment also redistributed the Moon's mass unevenly. Some regions became denser because of compressed melt pools, while others became lighter due to brecciated, fractured surfaces. These mass imbalances eventually contributed to the Moon's mascons, mass concentrations hidden beneath the maria that later spacecraft detected by tracking gravitational anomalies. These mascons, rooted in the early bombardment era, still influence spacecraft orbits today, shaping the paths of future missions through subtle gravitational pulls. As the final waves of heavy impacts tapered off, the Moon began transitioning from a world defined by external violence to one shaped by internal cooling. The surface was now a chaotic mix of craters, basins, and fragmented rock fields. But beneath this rugged exterior, the mantle and core continued to solidify in relative quiet. The bombardment had written the moon's external story, but its inner world was beginning to settle into a long, slow geologic slumber that would last billions of years. The wounds of the bombardment remained open, exposed, and unhealed, but the forces that created them were fading. Even after the most violent period ended, smaller meteoroids continued to fall, but the overall intensity decreased dramatically. The moon finally had the opportunity to cool more uniformly, and its crust thickened enough to suppress large-scale volcanic resurfacing. What remained was a landscape carved by fire, crushed by stone, and frozen in place, a monument to the era when the solar system was young and restless. The moon bore every blow, preserved every scar, and emerged as an eternal witness to the chaos of planetary formation. In the calm that followed, the moon's battered surface began its long evolution toward the quiet world we see now. But that quietness hides the truth. Every crater, every ridge, every basin whispers the memory of the relentless cosmic hailstorm that shaped it. The early bombardment did more than sculpt the terrain, it forged the moon's character, irrevocably defining its surface, its interior, and its long-term fate. What began as molten fire became a world inscribed with billions of years of celestial history, written in the language of impacts, shock, and stone. Rapid cooling and the formation of the first lunar crust, a scarred canvas. After the violent infancy marked by colossal impacts and molten upheaval, the young moon began a gradual descent toward solidity. The vast magma ocean that had covered its surface started to lose heat to the void of space, its radiant glow slowly dimming against the black canvas of the cosmos. As temperatures dropped, minerals began to crystallize and float upward or sink downward, differentiating the crust into layers of varying density and composition. This process was uneven, punctuated by residual impacts, internal convection, and tidal heating, leaving the first crust both patchy and fragile. Even as it hardened, it bore the marks of its tumultuous past, a scarred canvas where the fingerprints of the early bombardment were still evident. The cooling didn't occur uniformly across the lunar surface. Some regions solidified faster, forming an early highland crust of plagioclase-rich minerals that would give the moon its characteristic light tones. Other regions remained semi-molten, with magma pockets persisting beneath thin crustal layers. These differences created tension in the developing lithosphere, leading to cracks, fractures, and weak zones that could later become channels for volcanic eruptions. Each solidified area was a testament to both the relentless forces of cosmic heating and the subtle art of crystallization, forming a latticework of primordial rock across the lunar surface. Impact events continued to intersect with the cooling process. Even as the magma ocean solidified, incoming meteoroids punctured the surface, melting crustal fragments and mixing them with newly formed minerals. Each collision acted like a brushstroke on the moon's early canvas, altering texture and color in localized areas. Some impacts were energetic enough to create melt ponds that later froze into distinctive geological layers, while smaller debris merely pulverized and scattered pre-existing crustal fragments. The cumulative effect was a surface etched with scars, cracks, and variations that recorded both the moon's fiery birth and its persistent vulnerability to the cosmos. Internal processes also shaped the crust's formation. Convection currents within the still warm mantle redistributed heat and materials, causing differential cooling. Denser minerals sank, contributing to the formation of a primitive core mantle boundary, while lighter minerals floated toward the surface to thicken the crust. This continuous churning prevented a uniform shell from forming immediately, giving the early moon a patchwork quality. It was a world in transition, shifting from a molten, chaotic entity to a more structured, layered planetesimal, yet retaining the memory of its violent origins through every uneven ridge and fractured plane. As cooling progressed, contraction of the crust became a noticeable factor. The solidifying rock shrank slightly, producing wrinkle ridges and faulted terrains across the moon's early highlands. These tectonic-like features, though modest compared to Earth's active plate boundaries, marked the surface with lines of stress that echoed the internal cooling processes. Each ridge and fracture was not just a physical manifestation but also a historical record, showing where the crust yielded to the combination of thermal contraction, tidal forces, and the lingering effects of early impacts. Over time, these features became permanent elements of the lunar topography. The first crust also began to preserve the Moon's earliest impact record. As solid rock accumulated, subsequent meteoroids struck harder and produced more defined craters. These craters, etched into a partially solidified surface, became deeper and longer-lasting than anything formed in the molten magma ocean. Each impact scattered debris across the surface, thickening the regolith and creating layers of breccia that were welded by localized melting. The scarred canvas of the Moon's crust was thus a dual narrative, both a record of external bombardment and an indicator of internal thermal history. Some regions of the protocrust developed particularly thick accumulations of plagioclase, forming the highland terrains that dominate the Moon's near and far sides today. These floating mineral rafts effectively insulated the interior, slowing further cooling. Beneath these highlands, residual magma pockets continued to simmer, occasionally breaching weak points in the crust. The interplay between hardened surface and molten sublayer created subtle undulations, fissures, and magma domes, which, once frozen, became part of the Moon's permanent texture. The result was a mosaic of hardened and semi-molten zones, each recording the Moon's formative struggle between solidification and internal heat. The initial cooling phase also influenced the formation of the earliest lunar basins. Massive impacts that coincided with cooling periods caused localized melting of the crust and mantle, producing vast depressions that would later become maria. These basins were initially flooded with molten material from the interior, which cooled into dark, basaltic plains. This process, beginning while the crust was still in transition, established a contrast between the bright, anorthositic highlands and the dark volcanic plains that would define the Moon's dual-faced appearance for billions of years. The scarred canvas was thus not uniform, but a dynamic patchwork of light and dark regions shaped by both cooling and impact. Volcanic activity was still active beneath the crust during this time. Magma chambers within the mantle periodically pushed molten rock toward the surface, exploiting fractures created by both cooling contraction and impacts. These eruptions were sporadic but contributed to the evolving texture of the crust, creating lava-filled pits and small volcanic domes. Though the lava flows were far less extensive than the later maria, they were instrumental in shaping the Moon's early relief. The crust's interaction with these molten intrusions reinforced the impression of a world that was neither fully solid nor entirely liquid, but a hybrid of resilience and malleability. The formation of the first regolith began as meteoroid bombardment continued on a partially solid surface. Fine particles produced by repeated impacts accumulated across the highlands, while breccia formed in crater floors and along fissures. This early regolith was coarse and uneven, different from the more uniform dust observed today, yet it laid the groundwork for the Moon's present-day surface. As the crust cooled, it became a repository of both thermal and mechanical history, capable of recording every subsequent strike and preserving a timeline of lunar evolution. Cooling rates varied depending on regional thickness and composition. Areas with thinner crust lost heat faster, forming solid rock earlier than the deeper, insulated regions. This disparity created stress differentials that manifested as fractures, ridges, and small faults. The Moon's surface, in effect, recorded its own cooling through structural imperfections that would persist for billions of years. These imperfections became the basis for the first lunar tectonic features, subtle though enduring, etched across the scarred canvas like geological brushstrokes. The process of fractional crystallization contributed further complexity. As minerals crystallized at different temperatures, They segregated within the magma ocean and near the crustal interface. Denser minerals sank to deepen the mantle, while lighter plagioclase floated upward to enhance the crust's thickness. This stratification, coupled with uneven cooling and impacts, created layered crust that varied in both composition and mechanical properties. The resulting heterogeneity gave the Moon its early structural resilience, allowing it to withstand subsequent bombardment while maintaining a visibly scarred, textured surface. As the crust solidified, contractional stresses continued to form wrinkle ridges and scarps. These features aligned with zones of weakness and fracture from earlier impacts, reinforcing the Moon's patchy, mosaic-like appearance. Unlike Earth, where plate tectonics redistribute stress over time, the Moon's rigid crust locked these early features in place, preserving them as permanent records of a rapid, violent formation process. Each ridge, fault line, and scarp became a historical marker embedded in the Moon's earliest crust. Thermal gradients also influenced crustal evolution. The contrast between cooling at the surface and lingering heat at depth drove slow, persistent circulation within remaining magma pockets. These currents shaped the mechanical properties of the upper crust, creating subtle variations in density and rigidity. Over time, these variations determined which areas would fracture more easily under the impact of meteoroids, influencing crater formation patterns and subsequent surface evolution. The Moon's scarred canvas was thus a record of both thermal history and external forces. The largest early impacts contributed to melting that locally reset the cooling clock. Basins thousands of kilometers wide reflooded with molten material, creating temporary magma seas that reworked the crust and created localized layers of newly formed rock. This resurfacing occasionally obscured earlier scars but also added new stratigraphic layers, allowing geologists billions of years later to reconstruct a chronological sequence of impacts and cooling episodes. The interplay between destructive impact and constructive cooling created a layered, multidimensional geological history. Residual magma beneath the crust occasionally erupted through cracks created during cooling. These eruptions were not continuous but episodic, producing domes, pits, and lava flows that contributed to the early surface relief. While small relative to later Maria, these events demonstrated that the Moon was still geologically active during the crust formation phase. The solidifying crust acted both as a barrier and a mold, shaping how magma emerged and cooled, leaving features that would be preserved for eons. The first lunar crust was chemically distinct from the interior. Plagioclase-rich anorthosite dominated the surface, while magnesium and iron-rich minerals sank to the mantle. This differentiation created a mechanical contrast, with lighter crust floating atop denser, semi-molten layers. The result was a fragile but resilient shell capable of supporting a record of impacts, thermal stresses, and minor volcanic activity. Even as cooling progressed, this shell preserved the scars of the early bombardment, becoming a historical canvas on which the Moon's formative years were permanently inscribed. By the end of this rapid cooling period, the Moon had transitioned from an incandescent, molten sphere to a partially solid, cratered world. Its surface was uneven, scarred, and heterogeneous, a patchwork of early highlands, nascent basins, and volcanic intrusions. Though still internally warm, the Moon's surface could now record the relentless violence of the cosmos. Every scar, every ridge, every crater became a permanent entry in the Moon's geological diary, capturing both the history of rapid cooling and the enduring mark of early bombardment. Even after the crust solidified, the Moon's near and far sides cooled at slightly different rates. The near side, warmed by Earth's residual heat, remained thinner and more prone to fracturing and later volcanic flooding. The far side, insulated and thicker, solidified more quickly and retained more of its primordial highlands. This early asymmetry created a foundation for the Moon's dichotomy, setting the stage for contrasting terrains that would define its appearance for billions of years to come. The scarred canvas was thus both a product of rapid cooling and a prelude to future geological differentiation. Crater morphology during this period also reflected the interplay of cooling and impacts. As the crust thickened, larger craters could form without melting the entire surrounding area. Impact melt still pooled locally, but solidified crust restrained the spread, creating distinctive rims, central peaks, and ejecta blankets. These early features formed the blueprint for future lunar geology, preserving a mixture of crustal texture, structural integrity, and impact history that would be studied by generations of scientists and astronauts alike. The formation of the first crust also marked the end of the Moon's global magma ocean phase. Though pockets of molten rock persisted, the surface was now solid enough to survive minor impacts without wholesale melting. This shift allowed for the accumulation of regolith, the preservation of early impact scars, and the initial establishment of highland elevations. The Moon's scarred canvas was no longer just a product of molten turbulence, it had become a permanent record of the interplay between heat, crystallization, and cosmic violence, a visible testament to the planet's formative years. The rapid cooling and crust formation phase left the Moon in a delicate equilibrium. Solidified enough to retain topography, yet still warm internally, it became capable of preserving the record of billions of years of impacts and internal processes. The first crust was a stage upon which future geological events, from mere volcanism to tectonic stretching, would play out. Its composition, structure, and scars would define the Moon's enduring identity, a scarred canvas reflecting both the violence of its birth and the gradual serenity of its slow cooling into a world that would accompany Earth through the eons. Distinguishing impact craters, circular rims, central peaks, ejecta blankets. On the Moon's scarred surface, craters stand as unmistakable testaments to cosmic violence, each one a miniature laboratory of physics frozen in stone. The most immediately recognizable feature is the circular rim, raised above the surrounding terrain as if the Moon itself had pushed back against the force of the impact. These rims are formed when the kinetic energy of a meteoroid's collision displaces surface material outward, creating walls that encircle the newly formed depression. The steepness and height of these rims vary depending on the size and speed of the impactor, revealing the energetic story of the collision that created them. Inside larger craters, one often finds central peaks, rising like islands in a sea of crushed rock. These peaks form due to the rebound of the Moon's crust immediately after impact. As the meteoroid strikes, it compresses the surface deeply. The sudden release of pressure causes a central uplift, similar to the splash of water rebounding after a stone hits its surface. The height and composition of these central peaks provide clues about the Moon's internal layers at the time of impact, sometimes exposing materials from deep beneath the crust that would otherwise remain hidden. They are windows into the Moon's interior, frozen in time. Surrounding both the rim and the central peak is the ejecta blanket, a chaotic spread of rock fragments hurled outward from the point of impact. This debris blankets the surrounding landscape, forming rays or asymmetric patterns depending on the angle of collision. The ejecta often consists of shattered crustal material, glassy melt droplets, and breccias fused by the immense heat of impact. Over time, subsequent smaller impacts and micrometeorite bombardment break down this material, contributing to the growth of the lunar regolith. The ejecta blanket is therefore not only a snapshot of a violent event but also a seed for the Moon's evolving surface. Smaller craters, though less visually dramatic, reveal the same essential features on a miniature scale. Their rims may be lower and less pronounced, central peaks absent, and ejecta blankets thinner, yet the mechanics of their formation mirror those of larger impacts. The distinction between simple and complex craters allows scientists to categorize them, often correlating size with the presence of features such as terraced walls or floor fractures. Even in miniature, these craters preserve the energy dynamics of the collisions that formed them, offering a granular record of the Moon's bombardment history. Impact angle influences crater morphology as well. When a meteoroid strikes nearly vertically, it tends to create a symmetrical circular crater, with evenly distributed ejecta. Oblique impacts, on the other hand, produce elongated shapes, asymmetrical rims, and lopsided ejecta blankets. By studying these variations, scientists can reconstruct the trajectory of impactors and better understand the distribution of meteoroid populations that struck the Moon over eons. Each crater, therefore, is not only a record of impact but a small archive of celestial mechanics and orbital dynamics. Some of the largest craters reveal multi-ring basins, a complex pattern of concentric ridges surrounding a central depression. These basins, such as the Imbrium or Orientale, are the result of colossal impacts so energetic that the crust itself flexed and fractured over hundreds of kilometers. The multiple rings represent zones of rebound and compression, a response of the lithosphere to extreme stress. Studying these formations allows scientists to infer the Moon's crustal thickness and mechanical properties during its formative period, effectively letting them measure the ancient lunar interior. Crater floors vary depending on both size and age. Young craters often have rough, irregular floors littered with blocky debris, while older craters may be partially filled with lava or regolith, creating smoother surfaces. Central peaks can evolve over time, eroding through micrometeorite impacts or subsidence of the crater floor. In this way, the morphology of a crater encodes both its creation and its evolutionary history, providing a layered timeline of lunar geological processes. By examining floor features, scientists can distinguish fresh craters from those softened and reshaped by eons of cosmic weathering. Ejecta patterns also preserve evidence of impact velocity. Faster collisions produce more widely dispersed blankets and longer ray systems, while slower impacts concentrate material closer to the rim. In some cases, secondary craters form when large chunks of ejecta land nearby, creating a chain of smaller depressions. These secondary craters are vital for understanding the dynamics of ejecta dispersal and the energy transfer during collisions. They transform the lunar surface into a network of nested scars, each telling part of a larger story of bombardment intensity and frequency. Crater terraces form in complex craters when the walls collapse inward under gravitational stress. These step-like formations indicate that the lunar crust was flexible enough to slump but rigid enough to maintain a layered appearance. Terracing varies with crater size and depth, providing additional clues about the Moon's mechanical properties. By mapping terraced walls, researchers can infer variations in crustal composition, revealing regions that may have been mechanically weaker or more fractured at the time of impact. Each terrace adds a subtle note to the Moon's symphony of scars. Impact melt pools are another feature found in many larger craters. When an impact releases enormous heat, the surface rock melts and flows across the crater floor, sometimes pooling into shallow lakes before cooling into solid basaltic sheets. These melt pools preserve chemical compositions of both crustal and sometimes deeper mantle materials. The study of these pools provides insight into the temperature, pressure, and composition of lunar materials during the impact, effectively giving scientists a snapshot of conditions within the Moon at the precise moment of collision. Rim height and slope are shaped by both impact energy and subsequent erosion. Steep, high rims often indicate younger craters or those formed by particularly energetic impacts, while lower, eroded rims suggest older formations modified by later micrometeorite bombardment and thermal cycling. Variations in rim height across the Moon help construct a relative chronology of impacts, showing which regions were most heavily bombarded at different periods. In this way, rims are not only physical barriers but chronological markers embedded in the lunar landscape. The size and morphology of central peaks also provide clues about crustal thickness and elasticity. Taller, more prominent peaks suggest a crust capable of rebounding significantly under impact stress, while smaller, subdued peaks indicate a more ductile response. Studying these variations allows researchers to map differences across the lunar surface, connecting visible features with subsurface structure. Central peaks are thus both dramatic visual features and diagnostic tools for understanding lunar geology. In heavily cratered regions, overlapping craters create complex interactions between rims, floors, and ejector blankets. When a new impact strikes an older crater, the collision can partially destroy the rim, bury the central peak, or redistribute the ejector. These superimposed features are essential for relative dating, as they allow scientists to establish a sequence of impacts over geological time. By analyzing overlapping patterns, the Moon's layered history can be reconstructed with remarkable precision, one crater at a time. Some craters exhibit ring fractures within their floors, resulting from shock waves transmitted through the crust during the initial impact. These rings are often concentric with the main crater and reveal zones of differential stress and rebound. Ring fractures sometimes control subsequent volcanic intrusions or lava ponding, linking impact processes directly with internal magmatic activity. Their presence demonstrates the interplay between surface bombardment and deeper geological processes, reinforcing the Moon's complexity beneath its seemingly inert exterior. The sharpness of ejector rays fades over time due to micrometeorite bombardment and space weathering. Young craters display vivid rays stretching for hundreds of kilometers, while older craters have rays that are broken, muted, or partially buried under regolith. By mapping ray systems, scientists can estimate relative ages, reconstructing the Moon's more recent bombardment history. The contrast between bright, fresh rays and subdued older ones adds a dynamic layer to the Moon's scarred canvas, highlighting the ongoing influence of small but persistent impacts. Crater floors can also contain slump features, where sections of the wall collapse inward post-impact. Slumping modifies the original bowl shape, creating terraces, mounds, and uneven depressions. The extent of slumping depends on wall composition, impact size, and internal crustal strength. By analyzing these slump structures, scientists gain insight into the Moon's surface stability and mechanical behavior, even long after the initial impact has occurred. Each collapsed section contributes subtle detail to the Moon's rich geological tapestry. Multicrater formations, such as chains or clusters, reveal the sequential or simultaneous impacts of multiple bodies. Sometimes these are secondary craters formed by debris ejected from a primary impact, creating radial patterns across the lunar surface. Chains and clusters add further texture to the Moon's topography and serve as markers for modeling ejector trajectories. The distribution of these features offers insight into both the energy of the original impact and the dynamics of debris dispersal in a near-vacuum environment, illustrating the Moon's exposure to a turbulent cosmic neighborhood. Some of the most fascinating craters are those partially flooded by basaltic lava, resulting in maria. These craters combine impact morphology with volcanic processes, leaving floors that are smooth and dark while preserving raised rims and sometimes central peaks. The interaction of impact structures with volcanic resurfacing demonstrates the Moon's duality, a surface shaped both by external forces and by its own internal heat. Studying these flooded craters provides essential clues about the timing and nature of lunar volcanism relative to bombardment. Secondary craters around large basins can appear as chains or clusters extending hundreds of kilometers. Their size and distribution help trace the direction and magnitude of ejector flow from the parent impact. Mapping secondary craters allows reconstruction of impact mechanics on a large scale, showing how one collision could reshape the terrain far beyond its immediate site. These secondary formations further enrich the Moon's complex crater record, linking distant features to singular catastrophic events. Craters also record subtle information about the Moon's environment at the time of impact. Differences in ejecta particle size, floor morphology, and rim composition can reflect variations in crustal temperature, density, and layering. By carefully analyzing these features, scientists can reconstruct not only the impact itself but also the properties of the lunar surface and near-surface interior. In this sense, each crater is both a consequence and a diagnostic tool, simultaneously shaped by and revealing the Moon's evolving geology. Terraced walls, central peaks, and ejecta blankets together create a multidimensional record of impact mechanics. The height of the rim, the angle of slopes, the volume and reach of ejecta, and the shape of the central peak all encode energy transfer, material behavior, and crustal response. By integrating these observations, scientists can model impacts with remarkable precision, converting lunar scars into scientific data. Each crater thus functions as a three-dimensional archive of cosmic violence, frozen in time. The degradation of crater features over time is equally informative. As micrometeorites, solar wind, and thermal cycling act on rims, peaks, and ejecta, the Moon's surface evolves subtly, eroding older features while preserving younger ones. Observing these changes allows researchers to calibrate crater ages, reconstructing the chronology of bombardment across the lunar surface. The slow weathering process transforms the Moon into both a laboratory of impact mechanics and a record keeper of time. Large multi-ring basins, such as Orientale, illustrate extreme manifestations of impact morphology. Rings of concentric ridges extend hundreds of kilometers, while central depressions display complex interactions between impact energy and crustal response. These structures are invaluable for understanding how the Moon's crust behaved under extreme stress, revealing mechanical properties and regional differences in crustal thickness. Multi-ring basins are the Moon's grandest craters, monuments to the most energetic events of its history. Even small craters provide significant insights. By comparing shapes, ejecta distribution, and interior features across size scales, scientists can refine models of impact physics, apply scaling laws, and better understand lunar geology. The accumulation of small crater data enhances the interpretation of larger, more complex features, showing that every crater, regardless of size, contributes to the Moon's overall geological story. Each rim, peak, and ejecta blanket is a line in the Moon's autobiography of impacts, creating a tapestry of scars that narrates billions of years of celestial encounters. Evidence from Apollo samples, shocked minerals and impact melts. When the Apollo missions returned lunar rocks to Earth, scientists were presented with physical testimonies of a violent past. Among these samples, shocked minerals immediately captured attention. These crystals, deformed at the atomic scale, recorded pressures far beyond any terrestrial processes. Quartz and plagioclase grains displayed planar deformation features, microscopic layers within the crystal lattice caused by sudden, extreme pressure from meteoroid impacts. These features could only form under conditions of immense shock, providing incontrovertible evidence of the Moon's bombardment history and the violent forces that shaped its surface over billions of years. Impact melts were another compelling revelation from Apollo samples. These rocks, once solid crust, had been instantaneously liquefied by the kinetic energy of collisions. As molten material cooled rapidly, it formed glassy textures, vesicles, and unique mineral assemblages unlike anything formed under normal volcanic processes. Studying their composition allowed researchers to deduce both the temperature and pressure conditions of the impacts that produced them. The diversity of melt types suggested a wide range of impact energies, from small meteoroids to planet-sized projectiles, highlighting the relentless intensity of lunar bombardment throughout its early history. The presence of breccias in the Apollo collection further illuminated the Moon's violent adolescence. Breccias are rocks composed of angular fragments cemented together by heat and pressure. Many contained pieces of earlier crust, impact melt, and even smaller breccias, creating a complex stratigraphy within a single sample. This patchwork reflects repeated collisions, where material from multiple impacts was smashed, fused, and redeposited. These rocks, therefore, serve as microcosms of the lunar surface, capturing multiple events in their chaotic, interwoven textures and preserving a layered record of geological processes spanning hundreds of millions of years. Microscopic analysis revealed additional subtleties within shocked minerals. Some grains contained multiple sets of planar deformation features, each set corresponding to a separate impact event. This layering indicates that individual mineral grains survived repeated shocks, recording a sequence of cosmic collisions over immense spans of time. By counting and dating these features using radiometric techniques, scientists could reconstruct the frequency and timing of early bombardment, revealing a previously inaccessible timeline encoded within the Moon's rocky crust. Each mineral became a microscopic historian, narrating episodes of violence in atomic detail. The chemical composition of impact melts was also instructive. Variations in iron, magnesium, calcium, and trace elements allowed researchers to trace their source regions within the crust or upper mantle. Some melts originated from surface plagioclase, while others incorporated material from deeper layers, thrust upward by the force of impacts. By analyzing isotopic ratios, scientists could identify the relative contributions of different layers, revealing how impacts mixed and redistributed lunar material. These melt rocks, therefore, were not only evidence of destruction but also clues to the Moon's internal structure and chemical differentiation. Many Apollo samples exhibited features indicative of extreme thermal gradients. Rapid heating and cooling during impact events produced quenched glass alongside partially crystallized minerals. This juxtaposition suggests that collisions could instantly melt rocks, then allow some areas to solidify almost immediately, while adjacent fragments remained partially molten. The resulting textures provide a visual and microscopic record of dynamic processes that occurred in seconds, capturing violent events frozen in time. The heterogeneity of these samples demonstrates how single impacts could create a spectrum of conditions within a small area, each leaving a distinct signature in the rock. Evidence from these samples also included shock veins, tiny fissures filled with melt formed along fractures in rocks. These veins often cut across multiple mineral grains, acting as conduits for molten material during high-pressure events. The presence of these veins shows how impacts reorganized the microstructure of lunar rocks, redistributing heat and material in rapid, catastrophic ways. Their analysis informs scientists not only about the intensity of specific impacts but also about the mechanical behavior of lunar crust under extreme stress, bridging microscopic observations with planetary-scale processes. Some rocks contained high-pressure polymorphs, minerals that only form at extreme pressures. Examples include coesite and stishovite, forms of silica that are denser than the quartz we find on Earth. Their presence in lunar samples confirmed that collisions created shock conditions comparable to the most extreme pressures in terrestrial laboratories, demonstrating the Moon's exposure to energies far beyond typical volcanic or tectonic activity. These polymorphs act as pressure gauges, enabling researchers to estimate the force of ancient impacts and contextualize them within the Moon's geological timeline. The layering and composition of breccias also revealed repeated cycles of impact and regolith formation. Fragments from older impacts were incorporated into new breccias, often containing small glass spherules produced by molten ejector cooling mid-flight. These microglass spheres testify to the high-energy ejection of material from crater sites and its subsequent redeposition. By studying these spherules, scientists could reconstruct aspects of ejector distribution, impact velocities, and the thermal histories of localized regions. The Moon's surface, in miniature, was being archived within each fragment. Isotopic studies of Apollo impact melts provided insights into the age of collisions. By measuring ratios of parent and daughter isotopes, such as uranium-lead or rubidium-strontium systems, researchers could assign absolute ages to the rocks. Many melts clustered around the late heavy bombardment period, approximately 3.8 to 4.1 billion years ago, confirming that the Moon endured a concentrated epoch of intense impacts. This temporal precision allowed scientists to correlate lunar events with early solar system dynamics, linking the Moon's geological record to the broader history of planetary formation and orbital migrations. The textural complexity of impact rocks also revealed the mechanics of shock metamorphism. Some mineral grains were fragmented or twisted, while others remained partially intact, forming a mosaic of deformation. These textures provide a physical record of both pressure and directional stress, illustrating how rocks responded to sudden, intense forces. By examining the orientation and patterning of these features, geologists could infer the directionality of impact waves and the relative energies involved, translating atomic-level distortions into macroscopic understanding of lunar collisions. Volcanic signatures were occasionally present in combination with impact melts. Some Apollo samples showed evidence of minor magmatic intrusions into impact structures, suggesting that the Moon's internal heat interacted with surface shocks. These interactions may have influenced the subsequent cooling rates of melt sheets or affected the crystallization pathways of minerals within impact zones. The coexistence of volcanic and impact processes in a single sample highlights the Moon's complex geological interplay during its early history, revealing a dynamic environment where external and internal forces interwove. High-resolution electron microscopy allowed scientists to examine shock-induced defects within individual crystals. Dislocations, stacking faults, and microtwins all testified to the violent deformation experienced by minerals during impact. These defects, often invisible to the naked eye, act as permanent markers of stress, capturing the intensity, duration, and even frequency of impacts. By analyzing the density and orientation of these defects, researchers can reconstruct a microscopic map of energy dissipation during collisions, offering unparalleled detail on the mechanics of lunar cratering. Some impact melts also contained vesicles, small bubbles trapped during rapid solidification of vaporized material. These vesicles record the presence of volatiles and the rapid degassing that occurs during hypervelocity impacts. Their abundance and distribution help scientists understand the interaction of heat, pressure, and vapor in shaping lunar rocks. Moreover, vesicles preserve information about impact temperatures and the speed at which molten material cooled, adding an extra dimension to the physical and chemical history recorded in these samples. Shock-metamorphosed feldspar grains were particularly common among Apollo samples. These minerals, often part of the Moon's original highland crust, displayed systematic lattice deformations, fracturing, and partial melting. Their preservation indicates that even primary crustal material could endure repeated high-pressure impacts, albeit with profound alteration. By studying the degree of shock in these grains, geologists could infer both the intensity of bombardment in different lunar regions and the resilience of crustal components under extreme stress, linking microstructure to planetary-scale events. Some breccias preserved evidence of multistage impacts, where fragments from earlier collisions were incorporated into later melts. This process created a layered archive within a single rock, capturing the chronological sequence of multiple violent events. The complexity of these samples allows scientists to reconstruct the Moon's impact history in remarkable detail, revealing not only isolated events but also patterns of repeated bombardment. Each multistage breccia is therefore a composite record, a layered testament to billions of years of cosmic violence. Glass spherules found within impact melts provide additional insight. Formed when molten droplets cool rapidly in near vacuum, These spheres preserve the composition of the original melt with minimal contamination. Their size, shape, and chemical signature help reconstruct the energetics of the impact, the dispersal trajectory of ejected material, and even the thermal gradients within the melt sheet. Collectively, these spherules serve as microscale witnesses to colossal events, offering a tangible record of processes that shaped the Moon's surface on a planetary scale. Some Apollo samples revealed clasts of mantle-derived material within impact melts, indicating that sufficiently energetic collisions could penetrate through the crust and excavate deeper layers. The presence of these deep-seated fragments allowed scientists to study portions of the Moon's interior without drilling, effectively using impact events as natural probes. These rocks demonstrated how surface processes, including catastrophic collisions, could temporarily breach the crust, offering direct glimpses of otherwise inaccessible lunar layers. The magnetic properties of some impact melts also recorded information about the Moon's past environment. Cooling of molten material in the presence of a magnetic field can lock in a record of that field's intensity and orientation at the time of solidification. Analysis of such remnant magnetization in Apollo samples provides insights into the Moon's ancient magnetic field and its evolution over time, linking impact processes to broader planetary dynamics and the Moon's early geophysical state. The grain size distribution within breccias and melts carries additional clues. Coarse fragments indicate proximity to the impact site and high-energy excavation, while finer particles suggest distal deposition or slower cooling. By mapping the size and composition of clasts, scientists can infer the spatial distribution of ejecta and the mechanics of the impact, allowing a reconstruction of both local and regional effects of collisions. These microscale observations translate into macroscale understanding of lunar surface evolution. Evidence of shock-induced melting also helps distinguish between primary impact products and subsequent alteration. By identifying quenched melt phases, geologists can separate features formed instantly during collision from those resulting from slower cooling or secondary processes. This differentiation is crucial for constructing accurate timelines and understanding the progression from initial impact to long-term geological evolution. Apollo samples therefore provide both the raw material and the analytical framework for reconstructing lunar history. Some impact melts exhibit compositional zoning, where minerals crystallized in sequence as the melt cooled. This zoning preserves thermal histories and cooling rates, allowing researchers to model the energy dissipation during impact events. The study of zoning patterns also illuminates the chemical evolution of lunar material under extreme conditions, revealing how high-pressure melting influenced mineral segregation and rock formation. Such observations underscore the intricate interplay of chemistry, physics, and impact dynamics captured in Apollo samples. The preservation of these shocked minerals and impact melts is a testament to the Moon's lack of atmosphere and tectonic activity. Unlike Earth, where erosion, weathering, and plate movements obscure ancient scars, the Moon retains these fragile features for billions of years. Apollo samples, therefore, offer a near-pristine record of impact processes, preserving information that would have been lost elsewhere. Each grain, melt, and breccia is a physical chronicle, enabling scientists to piece together a detailed history of lunar bombardment, crustal response, and planetary evolution. The Late Heavy Bombardment Theory, a period of intense, widespread cratering. The concept of the Late Heavy Bombardment, LHB, arises from the observation that many of the Moon's large impact basins formed within a relatively narrow window of time, roughly 3.8 to 4.1 billion years ago. Apollo samples provided crucial evidence, as numerous impact melts and breccias clustered around this period. The LHB suggests that the inner solar system was subjected to a sudden spike in meteoroid and asteroid impacts, far exceeding the typical rate expected from gradual collisions. This proposed surge reshaped planetary surfaces, particularly the Moon, leaving scars that are still visible today. The theory of LHB initially drew attention because it offered an explanation for the apparent age clustering of lunar basins. Radiometric dating of Apollo rocks revealed that while some older surfaces dated back to around 4.3 billion years, many prominent basins like Imbrium, Nectaris, and Serenitatis appeared to have formed within a relatively short geological window. The coincidence of these ages suggested a systemic phenomenon rather than random, isolated impacts. Researchers proposed that a destabilization of small bodies in the early solar system led to a bombardment cascade, concentrating impacts across the inner planets during this epoch. Astrophysical models later provided potential mechanisms for the LHB. One hypothesis, known as the NICE model, suggests that the migration of the giant planets Jupiter, Saturn, Uranus, and Neptune reshuffled the outer solar system. As their orbits shifted, gravitational interactions perturbed populations of asteroids and Kuiper belt objects, sending them inward toward the terrestrial planets. The Moon, being unprotected by atmosphere or significant geological activity, bore the brunt of these collisions, recording them as basins and craters. LHB thus connects planetary dynamics on a solar system scale with localized geological evidence on the Moon. The LHB left a distinctive signature across the lunar surface. Large basins formed rapidly, with thick ejecta blankets spreading for hundreds of kilometers. These impacts generated enormous shock waves, producing widespread breccias and melt sheets observable in Apollo samples. The concentration of such large-scale features during the proposed LHB period differentiates it from the more evenly spaced, random cratering of earlier or later epochs. By analyzing the size distribution and frequency of craters and basins, scientists can map the intensity of bombardment, revealing the global influence of this extraordinary period. Evidence for LHB also comes from the Moon's far side. While early Apollo missions primarily sampled the near side, orbital mapping has revealed that many ancient basins on the far side share similar ages. This hemispheric consistency supports the idea that the bombardment was a solar system-wide phenomenon rather than a localized anomaly. It suggests that gravitational disturbances affecting asteroid populations acted globally, ensuring that both visible and hidden lunar terrains endured intense impacts, leaving a near-complete record of this violent era. Radiometric dating of impact melts forms the backbone of LHB chronology. Uranium lead, rubidium strontium, and argon-argon methods provide precise age constraints for rocks associated with large basins. Many melts cluster tightly around 3.9 billion years, supporting the hypothesis of a concentrated spike rather than a prolonged period of moderate impacts. This clustering is key to distinguishing LHB from background cratering, as it shows a statistically significant departure from the otherwise relatively steady pace of meteoroid collisions across the early solar system. The LHB hypothesis also explains the apparent scarcity of very ancient basins. Surfaces older than 4.1 billion years are relatively rare, not necessarily because impacts were infrequent, but because subsequent heavy bombardment during the LHB erased or reset earlier features. Craters from pre-LHB times were likely obliterated or heavily modified, leaving only fragments preserved in breccias or as subsurface relics. This creates a distinctive reset in the lunar crater record, where a dense cluster of mid-age features dominates the landscape. Modeling studies of LHB dynamics show that the bombardment involved both small and extremely large projectiles. While numerous kilometer-scale meteoroids created standard craters, larger bodies, tens to hundreds of kilometers in diameter, generated multi-ring basins. These mega-impacts had profound geological consequences, producing vast melt sheets, fracturing the crust, and possibly altering the Moon's thermal evolution. By connecting crater size to impact frequency, researchers can reconstruct the intensity and energy spectrum of the LHB. Geochemical evidence from Apollo breccias complements crater counting. Many samples contain shocked minerals and melt veins that date specifically to the 3.8 to 4.1 billion year window. The chemical composition of these materials reveals high-pressure formation, confirming that the rocks formed under conditions consistent with massive, rapid impacts rather than slow geological processes. The correlation between radiometric age and shock evidence strengthens the case for a period of concentrated bombardment. The LHB may have had implications beyond the Moon. Mercury, Venus, and Mars also exhibit evidence for an ancient spike in impacts. While erosion and tectonics obscure some records on Earth, the Moon provides a relatively pristine archive. The synchronous timing of craters across multiple planetary bodies implies that the LHB affected the inner solar system broadly, hinting at systemic orbital or gravitational disturbances that temporarily destabilized populations of small bodies. Some researchers propose that LHB was punctuated, not continuous. The bombardment may have occurred in waves, as different populations of bodies were destabilized at varying intervals. Each pulse would generate clusters of impacts, producing new basins while overlapping previous features. Evidence for this episodic nature comes from the subtle spread of ages in melt rocks and ejecta deposits, which, while concentrated, show minor variation, suggesting a series of successive waves rather than a single monolithic event. Theoretical work suggests that the timing of LHB might have played a role in shaping Earth's early environment. Intense bombardment on the Moon implies that Earth also endured frequent impacts, though obscured by erosion and tectonics. Such collisions could have influenced the early atmosphere, crust formation, and the delivery of volatile compounds. The Moon thus acts as a proxy, preserving a clearer record of bombardment intensity that helps infer the broader impact history of terrestrial planets. Analysis of basin morphology supports LHB timing. Many large basins share similar structural characteristics, including ring spacing, rim height, and melt sheet thickness. These similarities suggest formation under comparable conditions, supporting a clustered formation period. Differences among older and younger basins indicate variations in crustal temperature and lithospheric thickness at the time of impact, reinforcing the idea that the LHB occurred during a specific phase of lunar thermal evolution. Computer simulations of impact flux during the LHB reproduce the observed density and distribution of basins. By modeling the dynamics of asteroid populations perturbed by planetary migration, researchers can match the frequency, size, and timing of impacts on the Moon. These simulations suggest that thousands of objects, ranging from small meteoroids to massive planetesimals, may have struck the Moon over tens of millions of years, delivering enough energy to reshape its crust significantly. The LHB theory also explains certain anomalies in lunar rock ages. Some impact melts appear younger than expected, while others are older. The concentration of ages around 3.9 billion years indicates that most massive impacts occurred in a compressed time frame, while outliers represent either earlier background impacts or later, less energetic events. This age clustering is a defining feature of LHB, differentiating it from the more random, low-intensity cratering observed before and after this epoch. The implications of LHB extend to planetary differentiation. Repeated massive impacts may have influenced the Moon's crust-mantle boundary, redistributed heat, and triggered localized partial melting. Some basins were sufficiently deep to excavate lower crustal and even mantle material, as recorded in Apollo samples. These excavated materials reveal previously inaccessible chemical compositions, giving scientists a glimpse of the Moon's internal structure shaped by both impacts and subsequent cooling. Evidence from crater ray systems also complements the LHB framework. Bright rays radiating from young basins indicate the dispersal of ejecta over long distances, while older rays fade or are buried. By correlating ray preservation with radiometric ages, scientists can refine LHB timing, establishing which basins formed during the intense bombardment period and which belong to earlier or later phases. Rays, therefore, serve as additional markers of impact chronology. Some models suggest that LHB may have been initiated by the destabilization of resonant asteroid belts. Gravitational interactions between migrating giant planets could have shifted orbital resonances, sending swarms of bodies toward the inner solar system. This resonance sweeping could explain the simultaneous onset of high-impact flux on the Moon, correlating well with the concentration of radiometrically dated basins. The theory ties together orbital mechanics with physical evidence preserved on the lunar surface. LHB impacts were likely energetic enough to affect the Moon's thermal evolution. Massive basin-forming collisions injected heat into the crust, producing extensive melt sheets and temporarily increasing local crustal temperatures. These thermal pulses could have facilitated later volcanic activity, including the formation of maria, by weakening the crust and allowing basaltic flows to reach the surface. The LHB therefore not only sculpted topography but also influenced subsequent internal processes. The stratigraphic relationships of basins provide additional support for the theory. Younger craters often overprint older structures, while ejecta blankets from large impacts drape across multiple terrains. Careful mapping of these overlapping features allows scientists to construct a relative sequence of events consistent with a late, concentrated bombardment. This stratigraphic record reinforces the notion of LHB as a distinct period in lunar history rather than a gradual or sporadic increase in impacts. The LHB also reshaped the distribution of lunar highlands and maria. While the initial highlands formed before the bombardment, large impacts created basins that would later be flooded by basaltic lava. This sequence links LHB events to the geological contrast between the Moon's bright highlands and dark maria. In essence, the concentrated bombardment provided the depressions that later volcanic processes would exploit, transforming the Moon's topography on a regional scale. Apollo core samples drilled in basin regions reveal layered deposits consistent with LHB impacts. Thick sequences of breccia, melt, and regolith indicate repeated high-energy collisions, with some layers corresponding precisely to radiometrically dated events. These cores provide vertical records of bombardment intensity, supplementing the horizontal distribution of craters and reinforcing the global significance of the LHB. The LHB also affected the Moon's magnetic history. Some basins exhibit localized remnant magnetization, suggesting that impacts temporarily altered crustal and near-surface magnetic properties. These anomalies provide further constraints on the timing and intensity of bombardment, adding another dimension to the evidence collected from Apollo samples and orbital mapping. Modeling the size-frequency distribution of LHB impactors shows that the bombardment included both small, frequent meteoroids and rare, extremely large bodies. This range is consistent with observed crater sizes, from simple bowl-shaped depressions to multi-ring basins. The energy spectrum implied by these impacts helps quantify the total kinetic energy delivered to the Moon, emphasizing the extreme violence of this brief but formative period in lunar history. Comparisons with meteorites from other planetary bodies reinforce the LHB hypothesis. Certain asteroid fragments and Martian meteorites show signs of shock metamorphism dating to the same period as lunar basins. This correlation indicates that the LHB was a solar system-wide event, affecting multiple worlds and providing context for understanding the broader dynamical evolution of inner planets during the first billion years. Finally, the LHB remains a subject of active research and debate. Some scientists question the concentration of basin ages, suggesting that sampling bias or later resurfacing may influence the apparent clustering. Others explore alternative mechanisms, including stochastic impacts or local asteroid belt instabilities. Despite uncertainties, the combination of radiometric dating, crater analysis, Apollo sample chemistry, and theoretical modeling provides a compelling case that a late, intense episode of bombardment profoundly shaped the Moon and, by extension, the inner solar system during its formative years. Identifying volcanic features, smooth maria, rills, and domes. One of the most striking aspects of the lunar surface, when observed from orbit or through telescopes, is the contrast between the dark, smooth plains of maria and the bright, rugged highlands. These maria are vast basaltic plains formed by ancient volcanic activity. Their smooth appearance results from low-viscosity lava that once flowed across the surface, filling basins created by massive impacts. Over time, these lava flows solidified into basaltic rock, creating the expansive, relatively flat plains that dominate the near side of the Moon. Their dark color indicates a high iron and titanium content, distinguishing them from the anorthositic highlands. Rills provide another key signature of lunar volcanism. These long, narrow channels resemble river valleys but were formed by volcanic processes rather than flowing water. Some rills are sinuous, meandering across the lunar surface like winding streams, suggesting that they were carved by lava that traveled beneath a solidified crust or through collapsed lava tubes. Other rills are linear or arcuate, reflecting tectonic or volcanic subsidence. The variety of rill shapes encodes information about the temperature, composition, and flow rate of the lunar lavas, as well as the structural response of the crust during volcanic episodes. Lunar domes are subtle, rounded elevations that reveal more about the Moon's volcanic history. Unlike the expansive maria, domes are smaller, often measuring a few kilometers in diameter with gentle slopes. They are interpreted as the result of viscous lava extruding slowly from localized vents, building up gradually to form broad, low hills. Many domes contain central depressions that may represent vent openings, analogous to small shield volcanoes on Earth. Their morphology allows scientists to infer magma viscosity and eruption rates, offering insight into the diversity of volcanic processes on the Moon. The relationship between maria and underlying impact basins highlights the interplay between volcanism and cratering. Large impact basins created depressions in the crust that later served as natural reservoirs for lava flows. Basaltic lava filled these basins, smoothing over the irregular terrain and creating the familiar dark plains visible from Earth. This sequence indicates that many volcanic events were temporally and spatially linked to the Moon's impact history. By studying the thickness, extent, and composition of maria, scientists can reconstruct the timing and intensity of volcanic resurfacing relative to the impacts that shaped the basins. Flow features preserved on maria surfaces provide additional clues about eruption dynamics. Lobate margins, wrinkle ridges, and levees reveal how lava advanced and solidified. Wrinkle ridges, in particular, are compressional features formed as basaltic lava cooled and contracted, reflecting stress within the newly solidified crust. These structures provide a record of both thermal evolution and mechanical behavior of the crust during and after volcanic emplacement. By mapping ridges across multiple maria, researchers can compare regional differences in lava thickness, cooling rates, and crustal response. Sinuous rills, with their winding paths and meandering patterns, often originate from volcanic vents at the edge of a mare. Their curves suggest the movement of lava through channels that may have been insulated by a crust of solidified rock, enabling long-distance flows. In some cases, the rills exhibit collapsed sections, where the roof of a lava tube gave way, exposing the underlying conduit. Such features are direct evidence of subsurface volcanic plumbing systems and provide insight into the structural integrity and cooling behavior of lunar lavas over extended distances. Lunar domes often appear in clusters, suggesting localized volcanic centers rather than widespread effusive events. These clusters may indicate regions of prolonged volcanic activity, where repeated eruptions built overlapping domes. The spacing, size, and slope of domes can reveal information about magma supply rates and eruption duration. In some cases, domes are associated with small rills, suggesting that lava once flowed from the dome's vent through channels carved in the surrounding terrain, integrating dome formation with rill development. The spectral composition of maria helps differentiate them from highland terrain. Reflectance measurements show that maria basalts are richer in iron and titanium, giving them a darker tone, while highlands are dominated by lighter anorthosite. By analyzing spectral data from orbiting spacecraft, scientists can map the distribution of volcanic material and distinguish different lava flows, even where visual identification is challenging. This chemical information also informs models of the Moon's mantle composition and the sources of volcanic magma during different geological periods. Crater counting on maria surfaces provides insight into the age of volcanic activity. Smooth areas generally contain fewer superimposed craters, indicating that they were resurfaced relatively recently in lunar geological terms. By comparing crater densities across different maria, researchers can establish relative ages, reconstructing the timeline of volcanic episodes across the Moon. This method allows scientists to link volcanic activity with broader events, including the waning of the late heavy bombardment and changes in internal thermal conditions. Volcanic vents themselves leave subtle morphological evidence. Small pits, sometimes located at the summits of domes or along rills, mark the point of lava extrusion. These vents can be circular or irregular, depending on eruption style and local stress conditions. The alignment of multiple vents along linear trends suggests that tectonic structures may have guided magma ascent. Studying vent distribution helps scientists understand the interaction between stress fields, crustal fractures, and volcanic plumbing systems on the Moon. The thickness of lava flows varies significantly across different maria. Some flows are tens of meters thick, while others exceed hundreds of meters. Flow thickness influences cooling rates, thermal contraction, and subsequent surface morphology. Thick flows may form blocky or fractured surfaces, while thinner flows create smooth plains. By analyzing flow thickness, researchers gain insight into eruption volumes, effusion rates, and the ability of lava to fill pre-existing topography, such as impact basins and depressions. Wrinkle ridges on maria floors record compressive stresses induced by cooling and contraction. These ridges often extend for tens to hundreds of kilometers and can intersect or offset pre-existing craters. Their orientation and distribution reveal regional stress fields and crustal properties at the time of cooling. Wrinkle ridges are valuable for reconstructing the post-emplacement mechanical evolution of basaltic plains, demonstrating that even quiet lava flows experienced dynamic stress responses as they solidified. Some rills exhibit braided or branching patterns, reflecting variations in lava viscosity and flow rate. Wider channels suggest higher volume flows, while narrow, winding sections indicate lower volume or more viscous lava. These patterns preserve a record of the eruption dynamics, including turbulence, flow speed, and cooling gradients. By comparing rill morphology across different maria, scientists can infer changes in volcanic style and magma properties over time, revealing a nuanced volcanic history. Domes sometimes contain compositional layering, detectable through spectral analysis. Variations in mineralogy from base to summit suggest multiple eruption pulses or changes in magma chemistry during dome construction. Such layering provides evidence for episodic volcanism, where individual eruptions varied in temperature, viscosity, and chemical composition. Studying these compositional differences allows scientists to reconstruct the evolving nature of lunar magmatic systems. Volcanic cones on the Moon, though rare compared to Earth, are recognized in certain regions. These cones are typically small and steep-sided, formed from relatively viscous lava that solidified near the vent. Their presence indicates localized high-viscosity eruptions and contributes to understanding the diversity of volcanic activity on the Moon. By analyzing cone distribution, scientists can map regions of concentrated eruptive activity and link them to broader crustal features, such as faults or fractures. Some maria display flow fronts with lobate margins, showing the movement and final emplacement of lava. These fronts can intersect pre-existing craters or older flows, preserving a sequence of geological events. Flow fronts help reconstruct eruption directions, volume, and interaction with topography. They are visible both from orbital imagery and in some Apollo landing sites, providing tangible evidence of dynamic lava movement across vast distances. Volcanic vents and small cones are sometimes associated with pyroclastic deposits. These deposits result from explosive eruptions, where volatile-rich magma is ejected as fine particles. Pyroclastic layers provide insight into volatile content, eruption pressure, and the presence of gases in lunar magma. Such deposits, though less extensive than basaltic flows, contribute to understanding the diversity of lunar volcanism and the role of volatiles in shaping surface features. Rills sometimes form collapsed lava tubes, where the roof of a subterranean conduit gives way. These collapsed structures preserve the path of ancient lava flows, offering a three-dimensional record of volcanic transport systems. By mapping collapsed and intact tubes, scientists can estimate lava volumes, eruption rates, and the thermal insulation properties of lava conduits, enhancing models of lunar effusive volcanism. The distribution of domes across lunar maria is non-uniform. Some maria contain clusters of domes, suggesting prolonged volcanic activity, while others are devoid of such features. This variation reflects differences in mantle source regions, crustal thickness, and local tectonic stress. By correlating dome distribution with underlying geology, scientists can infer subsurface magma pathways and the influence of crustal structures on surface volcanism. Spectroscopic studies reveal that maria basalts vary in titanium and iron content. High titanium basalts are darker and often associated with younger flows, while low titanium basalts are lighter and generally older. These compositional differences provide clues about the mantle sources and evolution of lunar magma, indicating that volcanic activity was not uniform in either time or chemistry. By studying these variations, researchers can link surface features to deeper magmatic processes. Volcanic resurfacing also affected crater morphology. Pre-existing craters partially filled with lava become subdued, with floors smoothed and rims lowered. This interaction provides a relative age sequence, showing that certain craters predate volcanic flows. By examining these relationships, scientists can reconstruct a timeline of impacts and volcanism, demonstrating how volcanic activity reshaped the lunar landscape over millions of years. Some domes exhibit summit pits or depressions, which may indicate later collapse or continued venting after initial construction. These pits provide insight into post-eruption modification, magma withdrawal, or degassing processes. By analyzing pit morphology, scientists can infer the dynamics of dome evolution, including how subsurface structures responded to pressure changes and cooling. Rills cutting across highland regions suggest that volcanic activity was not confined to maria alone. In some areas, lava carved channels through older, anorthositic terrain, indicating that magma could penetrate beyond basins. These occurrences demonstrate that lunar volcanism was capable of interacting with diverse crustal types, contributing to localized resurfacing and structural modification even in rugged terrains. The thickness and areal extent of lava flows provide constraints on eruption volume. By combining surface mapping with gravity measurements, researchers can estimate flow depths and total lava volume, revealing that some maria represent massive volcanic effusions spanning hundreds of thousands of cubic kilometers. These calculations highlight the scale of lunar volcanic activity and its role in reshaping the Moon's surface during its thermal evolution. Some rills terminate abruptly in pits or depressions, suggesting that the lava channel ended in a subsurface reservoir. These terminations provide evidence for underground storage and transport of lava, offering a glimpse into the subsurface architecture of lunar volcanic systems. Understanding these conduits aids in reconstructing eruption mechanics and the efficiency of lava transport across the Moon's crust. Volcanic domes, rills, and maria collectively record a long-lasting period of effusive activity that spanned hundreds of millions of years. While the majority of activity occurred between 3.9 and 3.2 billion years ago, smaller eruptions continued sporadically afterward, gradually fading as the Moon's interior cooled. The spatial and temporal distribution of these features provides a comprehensive view of lunar volcanism, revealing both global patterns and localized anomalies. The interplay between volcanic and impact processes is evident where lava flows interact with cratered terrain. Lava may pond in basins, flow around crater rims, or partially bury pre-existing features. These interactions preserve a sequential record of events, showing that volcanism and impacts were interwoven forces sculpting the Moon's landscape. By analyzing these intersections, scientists can reconstruct both volcanic chronology and the relative timing of cratering events.